It looks like it's going to be on recording. Okay. Good afternoon, everyone. First ritual coming in, even though it's still rather smoky outside. I do think the smoke levels are coming down. There was a 165 AQI in Oakland last time I checked, and then it went down, so I don't have a number. But that's lower than it's been the past couple of days, so it is improving. All right. I'm going to bring up this PowerPoint. Because today we do have our exam. We're going to take the exam 3. As I said, the email is going to be a bit shorter than previous exams. It's going to be 75 minutes rather than 90 minutes for previous ones. It's going to be 25 multiple choice questions and 5 free answers. Essentially, it's shaved down a bit. We're going to use a little bit of extra time for a little bit of lecture. So we're going to talk a bit about light emission, starting to go into quantum mechanics. We're going to talk about emission spectra, the very specific different frequencies the different elements emit, which tell us sort of different things about composition of stars, for example, or microscopic samples. We'll be talking a bit, if we have time, about fluorescence, which certain materials will absorb high-frequency light, violet or ultraviolet, and emit much lower frequency visible light. Such that when you shine ultraviolet light on these fluorescent things, they glow with visible colors. We'll talk about sort of some things that do this. PowerPoint here. But before we start on these minor topics, I do want to take a few minutes for sort of last-minute questions in the exam. Not really a full review session, but just going over some questions that you guys might have about exam topics. Does anyone have any questions they wanted to go over before we jump into lecture? Are you good about this exam? Pumped up? Okay. Sort of. All right. Well, if that's the case, no other questions about the exam? Let's do a little bit of lecture then. Get through some of these topics. All right. So, here we go. We're now moving into the realm of quantum mechanics. And quantum mechanics really has effects mostly at very small scales. It deals with very small things, and its name, quantum mechanics, comes from the study of the very smallest pieces of things, which are called quanta. And even though quantum mechanics has these effects that are generally sort of very small scales, they have repercussions that show up on a very large scale and are very important to our lives. And interestingly, with quantum mechanics, at the very core of it is the idea of probability. There's probability sort of at the very core of quantum mechanics, and therefore kind of at the very core of our lives. We'll get into a couple of those more probabilistic ideas in just a little bit. For today, we're going to be discussing light emission, which has to do with the electrons in atoms moving between different energy levels in those atoms. So returning to the structure of atoms, I've introduced in the past, here's a slightly different, kind of more three-dimensional picture of an atom. The center of every atom is a positively charged nucleus. I'm just really going to be drawing a couple of protons here. There are also neutrons in that nucleus. And surrounding the nucleus are electrons. And the electrons in an atom are separated out into these shells, which are effectively at different distances away from the nucleus. So you have one shell where electrons can live that's very close to the nucleus at a certain distance, effectively. One shell that's a bit farther away. One shell that's still farther than that. And electrons live in these shells, and they don't really go anywhere in between. So you don't have any electrons in this sort of empty space between, or this space, or this space. This is a bit of a simplification. The real picture is a little more complicated, and the distances are not actually sort of exactly this, but this will do for the purposes of discussing light emission. So these shells, in which electrons live, effectively surround the nucleus at these various distances. So we have these shells like this. And depending on which shell they're in, electrons will have more or less potential energy. So electrons in shells that are farther from the nucleus, that are out here, for example, have a higher potential energy. Because if you let those electrons go and effectively let them fall into the nucleus, the ones farther out, the ones way out here, would do more work as they fell. And more of their energy can be converted into kinetic energy as they fell into the nucleus. Just the same way that a pen up here at a higher elevation has more potential energy than a pen down here at a lower elevation. If you drop this pen from higher up, it would do more work compared to this pen that you drop from lower down. The same way, electrons out here in the farther away shells have more potential energy. You can also think about it in terms of springs. If you stretch out a spring really far, it has more potential energy than if you stretch it out only a little bit. You can think about it in terms of a ramp. If you have a bowling ball on a ramp like this, when you have the bowling ball down here, it has a little bit of potential energy. But if you bring it up here, at a higher elevation, it'll do more work as it rolls down this slope. So a bowling ball up here will have a higher potential energy. But all these things are kind of an imperfect metaphor for electrons in an atom. Why is that? Why is this ramp with a bowling ball in it not a great metaphor for the potential energy of electrons in an atom? Anyone have an idea? This one's a little bit of a stretch. Yeah, why might that not be a great metaphor?
The electrons are constantly in motion.
Electrons are constantly in motion, that's true. Sort of. Again, there's a bit of a simplification that we make here. Electrons don't actually orbit the nucleus. They're not actually in motion in these clouds or these shells. But there are some complicating factors around that, that's true. An idea?
Is it because of the type of how the energy would be converted?
It's not necessarily because of how the energy would be converted. There are sort of different ways that you can convert energy from one type to another, right? If these electrons were allowed to just fall straight in, that energy would be converted directly from that potential energy into kinetic energy. But you could also see the energy being converted to thermal energy from collisions and things like that. So there are those considerations for sure. But the biggest difference here is that a bowling ball on a slope can be at any height, right? You can smoothly roll this bowling ball from here to here. And at every point in between, you'll have some amount of potential energy, some different amount of potential energy. But the electrons in an atom are a little bit different, because they only live in these very specific shells. So electrons can't be in between these shells. They can only be directly on them. So a bowling ball rolling up a slope is not a great metaphor. A better metaphor might be a bowling ball on a set of sort of uneven stairs. So to think about the energy levels of electrons in an atom, think about a set of stairs. They're not necessarily even. There we go. They have sort of a jagged shape like this. But the bowling ball can only be on one of these stairs. It can't be anywhere in between. So if the bowling ball is down here, it has a specific, fairly low potential energy. The bowling ball is up here, it has a different, but also specific, higher potential energy. It can't take any value in between. So one shell in this atom, let's see, there's blue here. One shell that represents the lowest stair with the lowest potential energy. Well, another shell might represent a higher stair with a higher potential energy. The electron in this shell would effectively be on that lowest stair, the lowest potential energy. The electron in this shell would be on a higher stair with a higher potential energy. I'm good so far? Okay. It should also be noted that different elements have different sets of allowed energy levels. They have different shells. In other words, different elements have different staircases. Depending on the element, the specific heights of these stairs can be different. You can have a different jagged staircase for a different element. We'll talk about the effects of that in just a little bit. Now, electrons don't necessarily always stay in the same shell all the time. If light of a specific frequency hits an atom, or if an electron, sort of rogue electron, hits an atom, or something else happens to an atom, one of the electrons can actually be moved from a lower stair to a higher stair. So you can have a situation like this, where here's a staircase. An electron starts off at a lower stair, and something hits it, something like light or another electron, and it bumps that electron up from a lower stair to a higher stair, like this. And when this happens, when an electron is bumped up from a lower stair to a higher stair, or from a closer in shell to a farther away shell, we say that the atom is excited. It's so happy to see its electron at a higher energy level. Unfortunately, this excitation is unstable and precarious in So most often when an atom becomes excited because one of its electrons has essentially been promoted to a higher energy level, it's unstable, and almost immediately that electron will fall back down, unfortunately. The electron will fall back down from that higher energy level to that lower energy level. And we call this de-excitation. But there's a problem here. That problem is that energy is conserved. So, when this atom becomes excited, when one of these electrons jumps up to a higher energy level, because something hit it. Some source of energy from outside came in, and energy from light or from some other electron came in and joined this atom. But now, when this electron is falling back down the stairs, falling back down to its original position, in doing so, the potential energy is going to go down, right? Electrons going down from a higher stair to a lower stair. Energy is going to go down. That can't happen, right? We can't ever have energy be created or destroyed. So when this electron falls down, that can't be the only thing that happens. But the only thing that happens, energy will be destroyed. So, when this electron falls down from a farther away shell to a lower shell, from a higher stair to a lower stair, it also spits out a pulse of light. Like this. This is a localized piece of pure energy. It's a particle of light, also known as a photon. So light emission is caused by this process. Atoms are excited when their electrons move from a lower stair to a higher stair. That's unstable, and so they're immediately de-excited. The electron moves back to its original shell, and in doing so, spits out this piece of light, a photon. And a photon is actually the smallest possible piece of light. You can't break light up into any smaller pieces than a photon. And so we sometimes call a photon the quantum of light. There's kind of a cool name for it. This piece of light is spit out, and that's how you get light emission. Any questions about this process generally? Yes?
So is this the only way that light is
This is the way that light is released from atoms. You have other ways of light being released if you have oscillating free electrons, for example. That will emit light. But this is sort of this is a major way that light is emitted. The only way it's emitted from atoms. Yes?
So you can assume that a photon is emitted from an electron at this photon is all the way down to another electron.
Yeah. So this photon may well hit another electron, might hit another atom, and cause this process of excitation and de-excitation again. That can absolutely happen again. You get sort of chains of this going on. All right, how's our timing? I want to start the exam at precisely 3:15, or let's see, not 3:15, 3:05. That'll give us 75 minutes. So we only got a couple minutes left before we want to get started on that. Let's talk about the energy of photons a little bit. All right, so these photons that are emitted by this process of excitation and de-excitation can't take on just any energy value. Because again, energy has to be conserved. Right? So when this electron drops back down to its original shell, its original spare, the energy of the light that it emits has to be the same as that difference. So generally, the energy of an emitted photon is equal to the energy level difference. Through which the electron fell. So photon energy is equal to energy level difference. And different kinds of light have different frequencies. We know that bluer light has higher frequencies. Ultraviolet light is higher frequency still. And then redder light has smaller frequencies, or lower frequencies, I should say. And infrared is lower frequency still. So different kinds of light have different frequencies. And bluer light, higher frequency light, is oscillating like this. It's oscillating pretty quickly. It's got a high frequency. Whereas redder light, lower frequency light, is oscillating like this. It's got a much lower frequency. Which do you suppose has a higher energy? It's going to be the bluer light, right? It's oscillating like this. Absolutely. And it's found, in fact, that the frequency of these particles of light, or these photons that are emitted by this process, the frequency is proportional to the energy. Or, sort of turning that around a little bit, photon energy is directly proportional to the frequency of that photon. That's worth putting it in a box. So higher frequency photons, higher frequency pieces of light, have higher energy. So, if we think about the possible photons that can be emitted by a certain element with a certain staircase. Let's say we have a staircase like this. Here's our lowest possible energy level, the shell that's closest to the nucleus. When a different piece of light hits this atom, it can take this electron up to the next stair up, or the stair above that, or the stair above that, etc. Take it up to any of these stairs. But when the electron falls back down to that lowest energy level, it's going to fall a different distance depending on which stair it started at. So there are these various different energy level differences in an atom. The electron can fall from here to here. When it does so, it will emit, actually we'll use black here. It will fall from here to here. When it does so, it will emit the, there we go, lowest possible energy of the photon this atom can put out. That'll be something like red light, possibly ultraviolet, or possibly infrared. If the electron falls down from here to here, it's falling a longer distance. It's falling from a higher energy down to this low energy. How is the energy of this photon going to compare to the energy of this photon? The higher energy, right? The electron's falling effectively farther. And because the energy of a photon is proportional to its frequency, the frequency of that photon is different. It will be a different color of light. So this drop might give you green light. This drop might give you blue light, some specific frequency. You can only have photons with these specific differences. You can also have differences in between these levels here. It's not just all the way from the top to the bottom. And each of those will give you a different frequency as well, but there are only these certain very specific frequencies of light that can be emitted by a certain atom. They don't emit every frequency of light, only very specific ones. And the specific set of frequencies that are emitted by a given element gives us it's called the emission spectrum of different elements. So every element has a unique emission spectrum, a unique set of frequencies that it can emit, which is kind of like a fingerprint for that element. So hydrogen will only emit this very specific red frequency here, this very specific kind of light blue, very specific darker blue. These get closer together, but they're still very exact. They're lines. Sodium is kind of cool. Sodium will only give us these yellow lines here. So sodium gas, when you put electricity through it, you excite that sodium gas by essentially zapping it. It glows very yellow. These are the only frequencies that it emits. So on. Neon gives you all kinds of low frequencies down here. What do you suppose neon looks like when you put electricity through it? Those low frequencies. Yeah.
Like an orangish color?
Kind of an orangish. In practice, since these even lower still frequencies are much stronger, it looks pretty red. So this set of different frequencies is the emission spectrum for various different elements. And these individual lines are usually called spectral lines. And they act like fingerprints. Alternatively, if you pass completely white light through a gas, so if you shine white light through, this looks like hydrogen gas, it'll give you a sort of full spectrum, your full rainbow, with a couple of lines missing. Those lines are missing because those frequencies of light are absorbed by that gas. So this is called an absorption spectrum. And the absorption spectrum is exactly the same as the emission spectrum, except essentially reversed. And we can make really good use of this absorption spectrum, because it also acts like a fingerprint for different types of materials. Use that on something like the sun, to figure out which elements make up the sun. So the sun gives us essentially white light, right? A full range of frequencies are visible. But if you look at it closely, if you analyze the light coming from the sun, you find that a couple of lines are missing. There are these individual frequencies that are missing from the rainbow of the sun. And if you take a look at those individually, you can pick out different elements that make up the sun. You can find all the lines for hydrogen. It's a hydrogen line. This is a hydrogen line. That's a fingerprint for hydrogen in the sun. You can pick out oxygen lines that are a fingerprint for oxygen. Iron lines that are a fingerprint for iron. And helium was actually first discovered in the sun. Astronomers looked up at the sun and analyzed this spectrum, this rainbow. So there were these missing lines and said, okay, this is oxygen, this is hydrogen, this is nitrogen. What the heck is that? There are these mystery lines that they'd never seen before that showed a new element.